The dominant narrative in the tech community claims that Linux is inherently a more secure choice than Windows. This belief, deeply rooted in the open source ethos, deserves a critical and rigorous analysis. This is not about demonizing Linux, a system that has revolutionized modern computing, but about deconstructing a myth which paradoxically can make users less secure. The argument I present is not iconoclastic by nature. It arises from a methodical observation of the operational reality we live in today. Cybersecurity is an empirical, not ideological discipline. It requires pragmatic evaluations rather than dogmatic allegiance. I myself have been a Linux user for over 20 years and a firm supporter of open source. Precisely because of this, I appeal to the true values of the community I belong to: freedom of thought, freedom of criticism, open-mindedness, and self-criticism. Not extreme dogmatism, nor the football fanatic-like behavior of those who cannot build a coherent argument. Let me be clear. Unstructured comments, intellectually lazy responses, blatant errors, or insults have no place here. Freedom of thought does not mean the freedom to spew nonsense. This video, in my humble opinion, represents a technically valid and intellectually useful contribution to the Linux community. Let's honor it with the level of discussion it deserves. When we analyze what secure by default really means, we must compare equivalent baseline states. A standard installation of Ubuntu 22.04 LTS presents characteristics that, from an operational security standpoint, are problematic. The UFW firewall is disabled by default. This decision, made to simplify the user experience, immediately exposes the system to network scans and potential exploitation of listening services. By contrast, Windows 11 enables Windows Defender Firewall by default with reasonably strict rules. AppArmor, Ubuntu's mandatory access control system, runs in complain mode for many critical applications, logging violations instead of blocking them. While this is understandable during testing, it becomes problematic when it reaches end users in production environments. Linux security suffers from a structural problem: ecosystem heterogeneity. While Windows has a centralized and consistent security model, Linux offers a mosaic of differing implementations. Debian Stable prioritizes stability at the cost of timely security updates. Arch Linux provides cutting-edge packages but sacrifices systemic stability. Ubuntu tries to compromise, often falling short on both fronts. This fragmentation is not a flaw of Linux itself. It's a natural result of decentralized open-source development. But from an operational security perspective, it represents a significant weakness. The Unix permission model, user group other, was designed in the 1970s. It is elegant in its simplicity, but woefully inadequate for the complexities of modern security requirements. Windows has evolved its security model with granular access control lists, ACLs, Active Directory for centralized identity management, group policy for configuration control, user account control, UA for privilege escalation. These mechanisms, while not perfect, offer far more sophisticated control than what most Linux systems implement by default. The sudo command is a perfect example of how a seemingly secure mechanism can create a false sense of protection. On most desktop configurations, sudo is set to grant unrestricted root access after a single authentication, often without proper timeouts or centralized logging. This transforms sudo from an access control mechanism into a mere procedural inconvenience. The user gets used to prefixing failed commands with sudo without understanding the real implications of escalating privileges. The myth of the protected minority. The argument that Linux is safer because it's less targeted reflects a shallow understanding of the modern threat landscape. This logic completely ignores enterprise servers, the cloud ecosystem, and IoT infrastructure, all areas where Linux dominates. Malicious actors, whether criminal or state-sponsored, focus on where the value and opportunity lie. Linux servers handle most of the global internet traffic, host critical infrastructure, and store sensitive data. The idea that these systems are ignored by attackers is empirically false. While open source is transparent in theory, in practice it exposes systemic supply chain vulnerabilities. The event stream incident in NPM, and more recently, targeted attempts to compromise Python projects, show how distributed trust can be exploited. Linux repositories hold tens of thousands of packages, often maintained by lone volunteers. Code review, when it exists, is rarely sufficient to detect subtle backdoors or sophisticated vulnerabilities. The democratization of software development comes with democratized risk. Windows 11 comes with Windows Defender, a built-in anti-malware solution providing real-time protection against known threats. It also includes ransomware protection, application sandboxing, integration with global threat intelligence. Linux, by contrast, offers no equivalent out of the box. ClamAV, often cited as the alternative, is mainly designed to detect Windows malware on email gateways, not to protect Linux systems from native threats. The philosophy of the system is secure, so it doesn't need protection, fails in the face of evolving threat vectors. Linux's sandboxing mechanisms, Snap, Flatpak, AppImage, are commendable attempts to modernize application security, but they come with significant limitations. Snap, controlled by Canonical, introduces centralization into an ecosystem traditionally proud of decentralization. Flatpak offers better isolation, but with default permissions that are often too loose. None of these systems match the maturity or deep integration of Windows Sandbox or App Container. Linux can be configured to reach security levels far above Windows, but doing so requires sysadmin-level expertise. AppArmor or C-Linux configuration, SSH hardening, firewall tuning, audit logging, these are not tasks for casual users. Windows, in contrast, has invested heavily in automating its security posture. The average user benefits from a reasonable level of protection without needing to become an expert. This philosophical difference has massive practical implications for real-world user safety. The belief that Linux is intrinsically secure leads many users to act recklessly. The absence of classic viruses has been misinterpreted as the absence of any threat. Linux users frequently install software from unverified repositories, run scripts from the internet without review, disable security features perceived as obstacles, avoid updates for fear of breaking compatibility. These behaviors, driven by a false sense of invulnerability, are often more dangerous than the threats Windows openly fights against. An analysis of critical vulnerabilities from recent years paints a clear picture. Shellshock, CVE 26271, compromised millions of Linux systems. Dirty Cow, CVE 2060-5195, affected virtually every Linux installation for a decade. Log4Shell, CVE devastating impact primarily on Linux servers. These aren't statistical outliers. They reflect systemic problems, complex software stacks, slow patching cycles, and unverified assumptions of security. Modern Linux malware, Mirai, Xort, Winty, shows increasing sophistication. Crypto miners silently hijack resources for months. Kernel-level rootkits evade traditional detection. State-sponsored attackers deploy Linux-specific toolchains. The narrative that Linux is immune to malware is empirically false and strategically dangerous. This analysis does not seek to demonize Linux or glorify Windows. Both systems have their strengths and weaknesses. However, perpetuating the myth of Linux's intrinsic security intellectually disarms users against real-world threats. Linux excels in transparency, flexibility, and customization potential. In the hands of skilled administrators, it can be more secure than any other OS. But that level of competence cannot be assumed in the average user, and security should not be a privilege reserved for a technical elite. The Linux community would benefit greatly from abandoning self-consoling narratives in favor of realistic evaluations. Recognizing current limitations is the first step toward overcoming them. Security innovation in Linux requires admitting its weaknesses, not denying them. Windows, with all its flaws, has shown that security can be democratized through automation and sensible defaults. If Linux wants to compete seriously in this area, it must evolve beyond the philosophy of the expert will figure it out toward models that protect the average user by design. Cybersecurity is too important to be subordinated to ideological preferences. It requires pragmatism, empirical evidence, and the courage to question even our most deeply held beliefs. All right, for those who have stayed, Welcome to the most technical part of this video. If you're not familiar with operating system research, capability-based security models, or formal verification methods, this might be a good point to stop. This section is aimed at security researchers, OS developers, and computer science academics. Let's start with an embarrassing confession for the Unix community. The traditional Unix permission model, owner, group, others, was designed for a small, trusted research environment. Even Dennis Ritchie acknowledged its simplicity was intentional for that context. But decades later, this legacy model remains at the core of systems far more complex than what it was built for. The most devastating critique comes from Butler Lampson in his famous paper, Protection, from 1974. Lampson identified what we now call the confused deputy problem. A privileged program can be tricked into performing actions the user never intended to authorize. The Unix model, based on identity instead of capabilities, is inherently vulnerable to this type of attack. Then there's Rob Pike. Pike and Ken Thompson, the same people who created Unix, completely abandoned the traditional permission model when they developed Plan 9 in the 90s. Plan 9 introduced per-process namespaces, where each process sees a different file system based on its specific privileges. This was an implicit admission that the Unix model doesn't scale for complex systems. Now fast forward to the present. Andreas Kling, with Serenity OS, is proving that it's possible to do better without completely breaking with the Unix legacy. Serenity OS implements a pledge unveil system inspired by OpenBSD, but taken much further. In this model, processes must declare their intended capabilities up front. Unlike Unix, where any process can attempt any operation and be denied, Serenity OS completely prevents the attempt. Here lies the fundamental philosophical difference. In Unix, you say, you can do everything except this. In Serenity OS, you say, you can only do this. It's the principle of least privilege implemented at the architectural level, not as a later patch. The unveil system goes further. It allows a process to make only specific parts of the file system visible. Once a process has called unveil, it literally cannot see the rest of the system. It's not a matter of permissions. Those files simply don't exist in its namespace. But if we want to talk about true alternatives, we need to look at pure capability-based systems, Kikos, Eros, and Koyotos. In Kikos, the concept of root user didn't exist. Every operation required presenting the appropriate capability token. You couldn't become root because root didn't exist as a concept. This eliminates entire classes of privilege escalation attacks. Eros, extremely reliable operating system, went further. It implemented persistent capabilities. Your system could crash and reboot, and all your capabilities remained valid exactly where you left them. It was security without sacrificing usability. Koyotos, Eros's successor, added formal verification. It wasn't just secure by design, it was mathematically proven that certain classes of vulnerabilities were impossible. But here's the paradox. These systems were technically superior to Unix in every measurable aspect of security, yet they failed commercially. Why? Software incompatibility. Decades of software written assuming Unix semantics couldn't run on these systems. Google Fuchsia is the modern attempt to resurrect these ideas. Fuchsia uses a capability-based model, but with a compatibility layer to run Unix-like software. It's a smart compromise, but time will tell if it succeeds where others failed. But maybe the problem isn't just permissions. Maybe the problem is we're thinking about security the wrong way. Systems like Flume and Highstar implement decentralized information flow control. Instead of asking who can access what, they ask where can this data go. In a DIFC system, every piece of information carries labels describing its sensitivity. As processes manipulate data, the labels propagate automatically. If a process reads a confidential file, that process becomes confidential. It can no longer communicate with the outside world without explicit declassification. This elegantly solves the confused deputy problem. Even if a deputy is tricked, it can't leak sensitive information because the flow control system automatically prevents it. Today, we see three main research paths trying to overcome Unix's limitations. Rust-based systems like Redux and Tok use Rust's type system as a security primitive. If the compiler can prove your code is memory safe, many vulnerabilities become impossible by design. Talk goes further. It implements capability-based scheduling where applications can't monopolize resources. Formal verification reaches its peak with CL4. It's the only microkernel in the world with a mathematical proof of functional correctness. Not, we hope it's secure, it's demonstrably secure by formal specs. The cost? Years of development per feature. WebAssembly-based isolation is a completely different approach. Instead of isolating processes, you isolate code. Every piece of logic runs in a WebAssembly sandbox with explicit capabilities. It's JavaScript sandboxing done right with native performance. So if we have all these technically superior solutions, why are we still using a 1970s security model? The answer is the compatibility versus security trade-off. We literally have millions of lines of code assuming Unix semantics. Migrating to a capability-based system would mean rewriting virtually every piece of software ever written. There's also the software ecosystem network effect. Developers learn Unix because that's what everyone uses. Companies choose Unix because they can hire people who know it. It's a vicious cycle of perpetuated mediocrity. And finally, the adoption chicken and egg problem. No one writes software for systems no one uses. No one uses systems with no software. The core problem isn't technical, it's ecosystem inertia. From a security perspective, we're using the equivalent of a Ford Model T to compete in Formula One. It works, but only because we don't have the courage to invest in change. And that perhaps is the most important point. Linux isn't insecure due to bad engineering. It's insecure because we choose compatibility with the past over security for the future. It's a choice, not a fate. Now let's move on to another pillar of Linux security that academic research has heavily criticized. The NetFilter iptables architecture, which forms the foundation of most traditional Linux firewall systems, including UFW, Firewall, and Shortwall. Back in 2000, Crispin Cowan and his team criticized the usability of Linux security tools, highlighting that many of them lacked formal verification and were hard to configure correctly. Although not naming iptables directly, the critique applies to the broader category of access control systems used at the time. 4 years later, Avishai Wool published a devastating quantitative study, a quantitative study of firewall configuration errors. The results were alarming. He found configuration errors in 37% of production firewalls. Linux iptables was particularly vulnerable to rule ordering mistakes, a problem stemming from the system's procedural rather than declarative nature. Wool identified the semantic gap, the distance between what the administrator intends and what iptables actually implements. It's like programming in assembly when you really need a high-level language. In 2012, Luigi Rizzo from the University of Pisa's CS department published NetMap, a novel framework for fast packet I/O, which systematically demolished NetFilter's performance. Rizzo demonstrated that linear rule traversal causes unacceptable N complexity, and that kernel user space context switching is inherently inefficient. Intel's DPDK team, between 2014 and 2016, published papers showing that NetFilter can't handle speeds above 10 gigabits per second. Their conclusion? Kernel bypass is necessary for high-performance networking. Traditional iptables is fundamentally unscalable. But the problem isn't just performance, it's architectural. NetFilter was designed for 100 megabits per second networks of the 90s, not for cloud computing and modern data centers. In 2021, a detailed performance study revealed serious flaws in Linux firewalls under heavy NAT and connection tracking loads. The paper concluded that iptables could not meet industry testing standards like RFC 2544. Meanwhile, multiple evaluations showed that iptables scales poorly with modern workloads. In large networks, rule processing time grows nonlinearly and CPU usage spikes rapidly. This architectural weakness has pushed many cloud providers to abandon traditional firewalls in favor of modern alternatives like NFtables and eBPF. A rule-based filter locked in a sequential model just can't meet today's demands. The eBPF revolution began with Brendan Gregg of Netflix in 2016. The extended Berkeley packet filter is a game-changer, programmable packet processing in kernel space with JIT compilation for near-native performance. No longer static filtering, it's dynamic computing over network streams. Facebook implemented Catron in 2018. a load balancer based on eBPF that completely replaces IP tables with 10x performance improvement over NetFilter. And the most interesting part? eBPF programs can be formally verified for correctness. Declarative firewall languages are a completely different approach. Timothy Nelson at Brown University developed the Margrave framework for formal firewall policy analysis with automated verification and conflict detection. Alex Story, also at Brown, took this to the next level with network configuration synthesis, automatic translation from high-level intent to low-level rules with proven correctness guarantees. It's like having a compiler for network policies. But perhaps the most fundamental critique comes from research on software-defined perimeters. The 2020 NIST SP 800-207 on Zero Trust Architecture explicitly states that authorization must move to the application layer. Google's Beyond Corp research goes further. It defines the traditional firewall model as fundamentally broken. The concept of a network perimeter is obsolete. Security must be based on device and user identity, not network location. Recent research directions are fascinating. The MIT Kinetic project from 2019 implements natural language translation to network policy with machine learning optimization and automatic conflict resolution. It's AI applied to network configuration. Stanford's frenetic language uses reactive functional programming for networks, with compositional policy construction and formal semantics for network behavior. It's mathematics applied to networking. On the hardware front, Intel DPDK and Xilinx AMD SmartNICs implement full packet processing in user space or FPGA, completely bypassing the Linux kernel. When the solution is to avoid the kernel, maybe the problem is the kernel itself. The academic consensus is crystal clear. iptables NetFilter is legacy architecture unfit for modern threats. Network-level filtering is insufficient. Application-level awareness is needed. Configuration complexity leads to vulnerabilities. Performance bottlenecks limit scalability. Zero trust models are replacing perimeter defense. As the 2020 NIST Zero Trust Architecture SP 800-207 explicitly states, the traditional approach of trusting users and devices based solely on network location is no longer sufficient. Authorization should be based on users and devices, not network perimeters. And here's the crucial point. We're not criticizing iptables because it's poorly implemented. We're criticizing it because the entire paradigm is obsolete. It's like using a typewriter in the age of word processors. It works, but you've missed the train of technological evolution. Academic research has already solved these problems. The solutions exist, are tested, and are superior in every measurable way. The fact that Linux still uses an architecture the scientific community deems obsolete is in itself a security problem. A potato rolls better than a banana. Sure, it's obvious. If you go to Russian Hill in San Francisco and try rolling a potato and a banana from the top, the banana won't even make it a meter, while the potato will keep rolling until it hits a physical obstacle. Physics rules apply. So, should we use potatoes for rolling? In cars, I see wheels connected to a mechanical system that allows steering, not potatoes. That's the point. We've always compared ourselves to Windows, the banana, and decided that anything better than Windows is automatically good. But that's not the way to approach security, nor is it a valid way to assess how secure a system really is. I compared Windows at the beginning precisely to show this paradox. Even an inefficient system with some basic invasive default settings can be potentially more secure than a potentially secure system that needs configuration, and, in the hands of the average user, is like the cockpit of a Boeing 777 in our hands. A potato rolls better than a banana, but that doesn't make it a wheel. Windows might have more immediate security settings than Ubuntu, but that doesn't make it a superior operating system. It just means Ubuntu has failed to provide sensible security defaults. The real benchmark shouldn't be better than Windows. The real benchmark should be secure for real users. When we measure security only by comparing to the worst system, we're setting the bar so low that anything looks like a success. It's like saying we're good runners because we run faster than someone walking. Cybersecurity requires absolute standards, not relative comparisons. A system is secure when it effectively protects the user using it, not when it's less bad than another system. The question isn't, Is it more secure than Windows? The question is it secure enough for real-world use? And if the answer for the Linux desktop in the hands of the average user is no, then we need to stop settling for, at least it's not Windows, and start working toward, yes, it is secure. The potato rolls better than the banana, but the goal is to build wheels. Allow me to close with absolute clarity to avoid any misunderstanding. This video is not an attack on Linux. It's a call for maturity in our community. Linux is not a failed operating system. It is an extraordinary technology that has revolutionized global computing. It powers 90% of supercomputers, most of the cloud, and practically all internet infrastructure. It's a triumph of human engineering we should be proud of. The problem is not Linux itself. It's our narrative around Linux. When we tell a new user, install Linux and you'll automatically be more secure, we're lying. Not out of malice, but out of intellectual laziness. We're selling a security that doesn't exist without expert configuration. Real security requires brutal honesty. Windows is full of flaws. We all know that. But at least it assumes the average user isn't a sysadmin. It automated imperfect protections instead of expecting users to become experts. We can do better. In fact, we must do better. Imagine a world where Ubuntu enables UFW by default with sensible rules, AppArmor operates in enforce mode for critical apps, mainstream distros implement robust sandboxing systems, users receive education instead of false reassurance. This isn't a betrayal of open source values, it's their evolution. Software freedom includes the freedom to be secure without becoming experts. Code transparency must translate into risk transparency. Community collaboration must produce solutions, not just criticism. To the distro maintainers listening, you have the power to change all this. You don't have to rewrite kernels or invent new tech. You just need the courage to adopt safer defaults, even if they're initially less easy. To users, stop settling for it's Linux so it's secure. Demand more. Learn more. Security is a skill, not an automatic consequence of OS choice. To fellow YouTube tech creators, stop perpetuating myths for easy views. Our responsibility is to educate, not falsely reassure. This video isn't the end of a discussion, it's the beginning. I hope I've helped shake some of our collective complacency. I hope I've shown that you can love Linux and criticize it at the same time. I hope I've demonstrated that true loyalty to something we love means wanting its improvement, not blind celebration. Linux deserves to be secure for everyone, not just the experts. Our users deserve the truth, not fairy tales. Our community deserves mature discussions, not tech religious wars. This is my contribution to the debate. Now it's your turn. Let's talk about it in the comments. But remember, freedom of thought, not freedom to vomit unformed opinions. This community is better than that. Thank you for having the courage to listen to the end.